Hi, I'm Jim Heffron. These are my lessons in Calculus 1. Today we're going to talk about continuity as an application of limits, so let's get started. All right, so I pulled a graph of a continuous, a graph of continuity in science off of the internet, just kind of a random graph. And I only want to make the point that here I'll focus on the temperature. This is the temperature of the air above of the atmosphere, above spot on the Earth, and you can see that the temperature, temperature falls for a while, rises for a while. Now, my point is that although the temperature changes, that you would be astonished to find that the temperature changes discontinuously. The temperature changes extremely rapidly. Suppose you were in an airplane 30,000 feet above the Earth, and then you went up, you went up by 100 feet, and the temperature dropped by 40 degrees. Okay, Celsius. That's an extremely radical change. It would have all kinds of physical consequences. So you'd say that can't be right. It must not be the case that the temperature changes that radically in a small space of time. It must be the case that the temperature is relatively smooth. That is to say, it must be the case that nearby altitudes have pretty much the same temperature. Of course, it's going to change, but nearby altitudes have not wildly different temperatures. Okay, now I want to take that principle and talk about it in mathematics. It's an extremely large topic in mathematics, and we're not only going to touch on it in a spot or two because we're going to need it. But this picture is supposed to give the idea of what happens in mathematics, and we're carrying over that same principle from the natural sciences, that if you have nearby inputs, in this case you're watching the two high wire walkers try to get past each other. If you have nearby inputs, so we're watching over time, the time is changing, then the values, in this case the positions of the two high wire walkers, have to be nearby. Of course they change somewhat, but if you go between time t equals 5 seconds and time t equals 5.1 seconds, the high wire walker can't just vanish from this spot and move to the other spot. They have to move smoothly. So these high wire walkers want to get to each other's ends. It doesn't matter. One of them can move quickly and the other one moves slowly. One of them can stand still for a while, whatever. But it cannot be the case that a walker on the left somehow jumps from x equals 2 to x equals 3. That is to say, although I don't know when or where, it might be at this spot here or it might be at this spot here, although I don't know when or where, they have to cross. Okay, so continuity is a principle that enables you to show that some things have to happen. In this case, for example, the two high wire walkers have to cross without knowing necessarily where it happens. There has to be an intermediate value, and again, I don't know which one, but there has to be some intermediate value. Is it here? Is it here? Is it here? I don't know which one it is, but there has to be an intermediate value where the two high wire walkers bump into each other. There just has to be. So now we're going to define continuity using limits, and the point is that enables me to accomplish two things. It first of all illustrates that limits are useful in places outside of the definition of rate of change function, and the second point is that it gives us practice with limits. Okay, so here we go. Definition of continuity. So here's a picture of a discontinuous function. We have a function where if you're standing here at the input x equals 1, then there's a spot where the function jumps up suddenly. The way that people sometimes talk about it is that you should be able to draw the curve without lifting your pen up off the paper. But in order to draw this graph, I have to lift my pen up and then come back down again. So I lifted it twice, and so that's a discontinuity. Now that's an informal definition, but brought back to the example from the natural sciences that I talked about a second ago, what we want is that if you take spots, come on, I'm having a little trouble with the pen. Come on, there we go. If you take spots that are near to 1, you're getting outputs that are near to 1, but all of a sudden at 1, you get an output of 2. If you take spots that are near to 1 but above, you have outputs that are near to 1. All of a sudden at 1, it jumps up to 2. So we want to avoid that. So we want to say that can't happen. So in a continuous case, that can't happen. Spots near to the anchor point have to have values that are near to the anchor point's value. And that's exactly what the definition says. The function is continuous at x equals a if the limit as x goes to a of f of x is f of a. Spots that are near to, so let's say, a minus 0.1, a minus 0.01, a minus 0.001. Spots that are near to a have to give you outputs f of a minus 0.1, f of a minus 0.01, f of a minus 0.001, have to give you values that are near to f of a. Okay, where f is defined near a. The function is continuous on an interval if it's continuous at each point in that interval. So this is pretty much an exact translation of your physical intuition. The first example is supposed to be a straightforward example that just isn't a polynomial. So I picked g of x as cosine of x, and I picked a equals pi just to pick something. There's a equals pi about 3.1. The graph makes perfectly clear, or said here with the pen, if I take values that are slightly less than pi, then I get, if I take inputs that are slightly less than pi, then I get outputs that are slightly less than f of pi. If I take inputs that are slightly more than pi, then I get outputs that are slightly different than f of pi. So it's perfectly clear here that the limit as x goes to pi of g of x is indeed f of pi. So in fact, the function is continuous on the entire real line. If I had chosen this for a, or this for a, or this for a, I would have come to the same conclusion. Basically, again, intuitively, I'm able to draw the graph without lifting my pen up off the paper. Hey, doing pretty good. Doing pretty good. All right, so it's a very intuitive idea, very natural, and I like to practice with the ideas, so I'm going to ask you to do a couple of these as practice. And again, the best thing you can do is to stop the video for a second and answer it. Write the answer down on a paper. Don't just say it to yourself, because it's very easy to convince yourself that you knew that. But so stop the video, write the answer down on a piece of paper, and start the video up again. So here we go. The function is 2 over x minus 1, and you're supposed to find the inputs, the x's, where the function is discontinuous. Not where the function is continuous, where the function is discontinuous. Okay, give you a second. Okay, and surely everybody thought with 2 over x minus 1, you've been trained to think x equals 1 is a spot that's going to give you trouble, and that's a good example. Okay, so for the second one, x over x squared minus 1, and again, I'll give you a second. You could stop the video. Okay, now this is an example where I sometimes have people have trouble. So I often have people raise their hand and say x equals 1, which is right, but they forget to say x equals minus 1 also. Minus 1 would also give you a 0 on the bottom of that fraction. So you got to take care of all the places where the fraction is going to give you trouble. Okay, next one. All right, great. And again, a person would think now, especially having been cautioned on the previous one, a person would think here, all right, so I'm going to figure out where is the bottom of that fraction equal to 0, and I'll write those down as the trouble spots. So good for you. Minus 1 and positive 3, because you can factor the bottom of that fraction, and it factors into x plus 1 times x minus 3. Okay, new one. Okay, great. This one's a little different than the others in that it's going to be an interval of numbers rather than just an isolated number or two. So with x minus 3 and then take the square root, you're asking yourself, I think you've been trained to ask yourself something like, what are the spots that are going to give me trouble? Well, they're the spots where x minus 3 is negative. So numbers like 2 and 1 and 0 are going to give me trouble, whereas numbers like 4 and 5 or 6 are not going to give me trouble. So I think a person would say here anything less than or equal to 3. Another one, x cubed minus 2x. Okay, great. And again, we all have this training that we all have gone through for many years. And looking at x cubed minus 2x, especially in the light of the previous examples, a person says, Really, there's no trouble spots, and that's exactly right. When the question is, where is this function discontinuous, the answer is that it's never discontinuous. You can say it another way. It's always continuous. Okay, next one, another square root. Okay, so I think a person is going to say to themselves with this one, under the radical there, that's going to be, if I multiply it out, that's going to be some kind of parabola. It's an upwards facing parabola because if you multiply the two x's together, you get x squared, and it's got a root at 1 and a root at 3. So I'll see if I can draw in the graph. How embarrassing. There we go. So we're looking at an upwards facing parabola that is negative on a certain range, and negatives are the trouble spots. So negative between 1 and 3. So I hope that folks have the reaction that between 1 and 3 are going to be the trouble spots. Okay, e to the x. Okay, great. And I think that, I hope that a person will remember what e to the x's graph looks like. The graph of e to the x is going to be something like so. And whatever a you pick, inputs near to a are going to result in outputs near to f of a. So in fact, e to the x is continuous everywhere. And one more here. This is one of those functions that's broken into two parts depending on whether x is less than 2 or x is greater than or equal to 2. Okay, great. And I think that the reasoning that a person would go through here is that x minus 1 is a perfectly innocuous polynomial, in some ways analogous to this. And x squared is another perfectly innocuous polynomial, so they're going to be continuous everywhere. The only spot I have to look out for is where they overlap. So I'm going to try looking at what happens at x equals 2. At x equals 2, x minus 1 gives you a value of 1. At x equals 2, x squared gives you a value of 4. So the overlap is the spot that gives you trouble. Okay. Okay, so basically the training that a person has seen for many years of these expressions where you've learned to watch out for certain things in the expression is exactly what's called for. To some vocabulary next, kinds of discontinuities. This is the example that we started off with, the x squared graph that has a sudden jump in it. That's called a removable discontinuity because if you wanted to, you could go in there and erase that one spot and color in this. Technically, all I'm doing is I'm saying it's x squared everywhere. And I've removed the discontinuity. So by doing some very minor surgery on the function, we are able to remove the discontinuity. Here's a function that I managed to cram two different kinds of discontinuities into one graph. So if you move along here, and then you suddenly jump up, that's called jump discontinuity. Took all day to think of that name. And the other kind of discontinuity here at a equals 3 is when the function goes infinite. In this case, it's minus infinity, but anyway, it's infinite. So that's cleverly called an infinite discontinuity. There is a point here that sometimes folks are not too familiar with this. I've had people come in from previous classes who say this is not the kind of thing they ran into. So I wanted to do a couple of kind of real life examples instead of the made up function from the previous slide. So this is the floor function on the top. The floor function is the greatest integer less than or equal to x. So if I say floor of 2.1, then you'd say, what's the greatest integer less than or equal to 2.1? You'd say that's 2. If I say floor of 1.9, what's the greatest integer less than or equal to 1.9? That's 1. And so there's a jump from 1 to 2, and you see that happening here. So at the at this spot, in this case a equals 2, at this spot you have a behavior where one thing is happening on one side and another thing is happening on the other side. If we were at not exactly at a equals 2, but instead of something like a equals 2.1, you'd say, well, it's continuous there. But it's at a equals 2 that you have some trouble. So a function is continuous from the right if the limit as x approaches a from the right of f of x equals f of a. It's continuous from the left if the limit as x approaches a from the left of f of x equals f of a. So you would say, for example, that this is a function right here. The floor function right here. I have trouble with the pen again. The floor function is continuous from the right because this is certainly continuous. It's continuous from the left, both at a equals 2, because this is certainly continuous. So continuous from the left and continuous from the right does not guarantee continuity. Here's an example of function square root of x minus 2. And of course, we've all been trained, so we all know to think that when x is less than 2, if x is 1 or 0 or 0.534, then you're going to run into trouble. This is a class in real number calculus, not complex number calculus, so we just ignore the complex case. So it's going to give us trouble. So we have a function that's continuous from the right. If you take values to the right, you're good, but of course if you take values to the left, you're no good. Okay. I want to summarize. We're not going to prove these things. We're not going to go down to the original definition of limits and prove each of these statements. But I want to summarize a kind of a global fact, because there wouldn't surprise anybody in the room that every one of these functions is continuous at every point in its domain, a polynomial function. So if I wrote down, and we had one earlier, if I wrote down a polynomial function, how about 7x to the fourth plus 5x? Now that's going to be continuous at every single input, because it's at every single real number, because every real number is in the input, is in the domain of that function. Rational function, if I said x over x minus 2, that's going to be continuous everywhere except for x is 2, and etc. Roots, trigonometric functions, inverse trigonometric functions like arc, tangent. Exponential functions, we saw e to the x there a little while ago. Logarithmic functions, ln, for example, come to mind. All of those functions are continuous at every point in their domain. So the sort of ordinary functions that a person has learned coming up to this spot are most often continuous. What about, so the basic objects are continuous. What about combinations of the objects? So if f and g are both continuous at a, then these functions are also continuous at a. C times f, f plus g, f minus g, etc. So for example, 7x squared is continuous because x squared is continuous, and so c times x squared, 7 times x squared, is perfectly good. If sine of x is continuous and square root of x is continuous, then so is the addition, and etc. So you're not surprised to find that the subtraction, the multiplication, and the division, provided, of course, that the denominator is not equal to 0, are all satisfy that if f and g are continuous, then f combined with g in any of these simple operations is also continuous at that spot. And then the last thing a person thinks about with function operations is function composition. So if g is continuous at a and f is continuous at g of a, then the composition f composed with g, which is the same thing as f of g of x, is continuous at a. So the only thing that happens here, I want you to pay just 30 seconds of attention here, is the reason that this says a and this says g of a. And of course what's happening here is that if you plug a into the function, then what g receives is an a, but what f receives is a g of a. So that's why I needed the change in the input clause. And I have a couple of examples, but they're perfectly natural. Sine of 3x is the composition of the sine function with the 3x function. Each of them is defined for any real number input. So the composition is defined for any real number input, so we're good. It's continuous on the entire real line. Similarly, e to the 5x is the composition of the 5x function with the e to the function, and so also continuous on the real line. And square root of 1 plus x is continuous anywhere where x is greater than, greater than or equal to 1. Greater than or equal to 1. There we go, greater than or equal to 1. It's not continuous at greater than or equal to minus 1. It's not continuous at minus 1, but it's continuous from the right. Okay. Greater than or equal to minus 1. And then I talked about being continuous from the right. So there we go. Continuous from the right with the equal sign. But if you want to be continuous, then you are erasing. There we go. It's not continuous from the left. Okay? Okay, very good. So so continuity is kind of a fast one, and we'll do a couple homeworks, but then we're going to go on and start taking derivatives of functions. Okay, very good.